So far, in this series, we've been talking about how to run probabilistic programs, right? So we talked about semantics, we talked about the denotational semantics, we also talked about operational semantics, and yesterday we talked a little bit about compiling probabilistic programs into tractable representations in order to reason about them, right? So today I kind of wanted to talk about something that is maybe I would say an orthogonal viewpoint on how to reason about probabilistic programs, which I think connects very nicely to the other kind of presentations that we've been seeing this week, which are program logics for deductively reasoning about probabilistic programs. So I wanted to talk a little bit about those today. So kind of the big motivation for, I think, the perspective that I'm going to show you on kind of probabilistic separation logic comes from an analogy between probability and mutable state. And I think really there's more in common with these two viewpoints than I thought at first. This was something that I learned that was new in the last couple of years. I really thought of these two things as being very, 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 very different. And over time, I've become more and more convinced that they have a lot in common. So this is really ongoing work that I think has kind of started with an older, well, not that old, OPLSS'24 paper from Barta, Su, and Liao on probabilistic separation logic. And really, the idea with this paper, and it was a really cool idea, is that in separation logic, we have all these rules for decomposing program state and reasoning about propositions modularly, right? And we have these what are called substructural connectives, star and wand, and we'll talk a little bit more about those. And the cool thing about the idea of probabilistic separation logic is that if I have a proposition P and Q on two sides of the star, what's that going to mean? That's going to mean intuitively that if I have some program state S, well, I'll say that S models P star Q. If I can split S up into two smaller independent S's, right? I split S up into two smaller independent S's, one of which models P and the other of which models Q, right? And if I can show that S1 and S2 are somehow independent, which you can denote with this perp symbol, and that S1 and S2 combine to give you something that's contained in S, then I have an interpretation for the symbol that somehow talks about state decomposition, right? And so the cool idea with this paper was, what if we think about this decomposition as a probabilistic notion, right? And how do we interpret what that means in a probabilistic context? And this has been a really interesting and ongoing active project. And I kind of wanted to tell you about the current state of affairs in these ideas. And in particular, I'm going to focus on a recent paper titled Lilac, a probabilistic separation logic for conditional probability. I don't even remember. We'll call it Lilac. And this is from John Lee, Amal, Ahmed, and myself. And I wanted to tell you what's going on in this paper today. And really, I think the main thing that I want to convey is that these two things are actually really quite analogous. And I think that's really, really quite beautiful and very, very interesting, right? So what is separation logic? I want to show you a little bit about separation logic. We've been using it a lot, and we've been using it at a high level. And I think it's good to pause and see some low-level examples of what it means. So at its core, separation logic is a program logic, which means it's something you can put in between the braces in a Hoare logic, right? So I can say, initially something is true, and then I'll assign x to alloc 10, right? So I'm working in a sort of imperative language. We're not probabilistic yet, right? This is my non-probabilistic imperative language where I'm allocating a fresh reference onto the heap. Right? That's what this symbol means. And then the post-condition for this is going to be that x points to 10. Right? That's what that means. Right? So this is a statement in a fragment of a logic that lets me talk about heap contents. And I can keep going. I can say that y gets alloc 20. Right? And then after I run that line, I can conclude something more about the program. I can conclude that x points to 10. And I can conclude that y points to 20. And what I've done is I've put a star in between them. Right? I put a star in between them. And what this star tells me is that x points to 10, y points to 20, and x and y are going to be true of disjoint. These two separate propositions are going to be true of disjoint parts of the heap. Right? So that means that x and y can't be aliases. Right? They have to be pointing to different parts of the heap. Right? Okay. And so separation logic has become an extremely successful and powerful tool within programming languages. It's used very widely, and we just saw in the previous talk examples of separation logic being used to great effect in imperative heap manipulating programs. Right? So I would consider this standard kit in the toolbox of reasoning about heap manipulating programs. Okay, I want to show you an analogous program. X gets flip 1/2. Okay, so I can think about this flip as like allocating a fresh random bit, right? So then I might have in my program logic ways of talking about randomness, right? I'm going to have a new kind of new propositions in my base logic for talking about what the result of running this program does, right? So you might want something like x follows Bernoulli 1/2, right? So that's kind of the analogous way of saying that x is, is a heap cell with referencing 10. Well, if I'm talking about probabilities, I want to talk about what the variables' distributions are, right? So I might be able to say x is a random variable that follows Bernoulli 1/2, right? That's the idea. And then if I allocate another random kind of bit, well, you're probably already thinking, okay, well, you're going to want to use star, right? X follows Bernoulli 1/2. And then star y follows Bernoulli 1/2. And what this star is going to mean is very analogous, right? The star is going to mean that these two things hold over disjoint portions of the state space of the program, right? And I think that the most intuitive way of interpreting that in a probabilistic content is that x and y, you would read this as x and y are independent, meaning statistically independent random variables, each following Bernoulli. Right? X and y are independent random variables, each following Bernoulli. Right? So this picture seems nice. We have this kind of fairly close analogy between the structural form of the programs and the structural form of the propositions. Right? And hopefully you're going to be able to get all the things you like about separation logic for something written in this so-called probabilistic separation logic. Right? So one of the things we really like about separation logic is this thing called the frame rule. Right? So the frame rule is the modular reasoning principle for heap manipulating programs. Right? So if I have a precondition P written in a separation logic, and then I run a command C, and then I get a postcondition Q, well, what if I go to all this effort to prove this little proposition here, and now I want to reuse it in the context of the rest of the program? Well, I have to be very careful. C might be referencing names that the other parts of the program might be touching. So in general, you may not be able to compose this into your program nicely due to the aliasing problem, right? So what I can show is, if I know, if I have some frame F, meaning this is some other independent piece of memory, then I can in fact show that this is true, right? Which is quite nice, right? If I can show that this is true in some small context, then it will continue to hold in a larger context as long as I'm independently framing on parts of the heap that aren't touched, right? This is the idea. And so what's really neat about this idea for separation logic that's been very successfully applied in heap manipulating programs where all of these stars are interpreted as non-overlapping heaps, if you just stick in independence for heap disjointness, you have a fully working thing, which is pretty awesome. So we're going to have to work through some details to get there. And I'm hoping to do that today. At least show you the intuition for the interpretation of base propositions. That's what I'm hoping to do. OK. So let's talk a little bit more about the semantic interpretation of heap manipulating propositions in normal separation logic. So this is normal separation logic for heap manipulating programs. OK, so there's going to be some ingredients. My configurations, meaning the things that my propositions are telling me things about, are going to be the pair store heap. Okay? So a store is a map from names to heap locations. And then my heaps are maps from, they're going to be partial maps, from location to values. Okay? So that's going to be like the data of my program, right? And I'm going to have various propositions that are going to be of the form SH is true for some, so this is a world. It's going to hold for some proposition like true, right? So what this means is you give me any store in any heap, and it's going to satisfy the proposition true, right? So that's the easy base case. And then another one, of course, it's not the case that any store and heap satisfy false. Okay. Some more simple cases. If you give me a store and a heap, well, certainly, if I want to show that two propositions hold in the normal conjunction, well, that's going to behave more or less like normal conjunction, right? I have to show that in order to show this, if and only if, it's the case that SH models P and the same heap, the same store model Q. Okay, so this is just your normal propositional interpretation if you like, right? Intuitionistic if you like. Okay. So in order to keep going, we want to talk in particular about this star. And I needed to use some extra symbols that I just threw at you, right? This disjoint, perpendicular, this union, this comparison, all this stuff needs to be defined. Because the game we're going to play is we're going to take each of these symbols and give them a probabilistic interpretation, right? So let's talk about what they are. So we're going to say that a configuration, two configurations are disjoint. We'll say these are disjoint if their heaps don't reference the same locations, right? So if the domain of H1 intersected with the domain of H2 is the empty set. Okay? So that's going to be our interpretation of perp, right? And then disjoint union. SH combines with S2H2. That's going to be defined as the disjoint union of heaps. Okay? So it's a partial function, right? This is important. It's a partial function, which is defined as you give me a location, right? And it's in H1 of L if the location is in the domain of the first one, H1. And we say H2 of L, or sorry, I need to be looking it up in the, it's like S of L to be properly type checked here, right? Because I'm going from names to heap locations. Actually, no, this is fine, yeah. H2 of L if L is in the domain of H2. Okay, and notice that this is partial because if I didn't know which heap L belonged to, then I wouldn't be able to give this a well-defined notion, right? I wouldn't be able to give this a meaning. Okay. And then the last piece that I need is a way to compare the combinations here. And I guess I should technically have put heaps alongside these, or it should be H. Did I go too fast? Yeah, I kind of went a little bit too fast here. It should be S1, S comma H1. And then this should be S comma H2. And then let's define it on configurations. S1 comma H1. And then the same thing will have to happen here. S1 comma H1 disjoint union S2 comma H2 less than S comma H. Okay, now everything type checks. And now we can define this thing. We'll say S1 is contained in S1H1 is contained in S2H2 in the intuitive way if every single location in this one is in this one and if they agree on everything, right? So if domain of H1 is equal to the domain of H2 and they agree. For all locations, we have that H1 of L should be subset. And then for all L1 in the smaller one, and S1 in H1, domain of H1, L1 in the domain of H1, we have that H1 of L is equal to H2. Okay, this is just saying the natural notion of subheap, right, is that for everything in the smaller one, they agree, right? Okay. So these things together give an interpretation for star, right, which I've already written over here. It says that S models P star Q if I can split these, if there exists some decomposition into two pieces that satisfy this requirement that I can combine them to get back the full picture, right? Any questions? This is like your whirlwind semantics of separation logic tour. Yeah.
The symbol for decomposition on the left, is the SH does not model, is that a bottom or is that a decomposition symbol?
This is supposed to be a decomposition symbol.
That was a decomposition.
Yeah, we can make this false.
Okay, thank you.
Yeah. Yeah.
So we do not have pointer here.
The pointers are, so the pointers are showing up here, right? So these are locations.
Oh, I mean the value we do not have pointer.
You could put them in there. Let's pretend they're not there. But yeah, it would be fine, right? Because you could make the, I didn't tell you what the values were. They could be locations, right? Nothing I've said so far would preclude that, though you would probably need to update this definition to be transitive under reachability and so on. Let's pretend you can't have that locations in there. It's a good question, actually. Yeah.
Why does the subheaping relation not worry about the names in the store?
Why does the subheaping relation not worry about names in the store? That's a good question. It has to do with like this sort of so the idea with these, it has to do with the interpretation of star that we're after, right? So the interpretation of star that we're after is I'm keeping the stores the same on the left and the right of the star, right? Because I want to be able to reason locally about the state, but perhaps I might want to still reason about names that are in the store, for instance, if they're pure, right? So I don't want to be splitting this store up unnecessarily. So it's useful to split the heap up into two pieces, but then keep the stores persisted on the two halves. And there's lots of different ways of writing this decomposition in separation logic. This is the one that's the most analogous to the generalization I'm going to show you. And different strategies of splitting this up will give you different kinds of substructural properties of this separation logic. So you can think about what would happen if you split the stores up and what that would do to your logic. I think, I don't want to say anything wrong. I think it like becomes intuitionistic or something. I'm not sure. There's something interesting that happens when you split that up too. People who know their separation logic trivia will probably know that one. Okay. Let me move over. Where do I want? I want more space. Let's work here. It's sad because it's all by analogy, and I hate to erase the analogous piece. Okay, let's draw our little table of analogies. Table of analogies, okay. So there are the various pieces, right? So like we have the, the meaning of, so we have the meaning of this guy, this plus. And we're going to have, I want to draw it this way. We're going to have our heap. And then I'm going to have prob. Okay. Right? And then I'll have my key semantic notions as the rows. Right? So this is disjoint union. For heaps, this U plus guy. It'll be something else for probabilities. And then we're going to have this thing, which is heap subsetting, or just subset. Right, that's going to be important. And then what else did we have? We had this thing, which is like heap disjointness. Right? And then I guess I should have given you one more thing, which was I gave you a program and I gave you a fragment in the logic and I didn't give that an interpretation. So let's give that an interpretation. We'll say S models X points to V if and only if H is defined on S H of S of X, and that equals V. Right? Okay. Right. So these are your so-called structural interpretations, and these are your like theory-specific interpretations. This one's for pointers, right? We're going to have a different one for probabilities. It'll be of these shapes, right? So I wanted to talk about this notion of ownership. So we're going to say that a portion of the heap is owned if a proposition kind of is it like how do I want to put this? So a portion of the heap is owned essentially if it can be referred to by the proposition, right? Ownership is a property of propositions. We say that like let's say name. So X is going to own a heap location. We'll say X owns a location L. Let's say I want this guy on the bottom to be ownership. And it's just going to be if the location L is in the heap. Okay, it's a fairly straightforward notion, right? I'm just saying a location is owned in the context of some proposition if it's in the heap. Okay. Now, we're going to need to give probabilistic analogies to each of these things in order to get a separation logic, right? And I want to stress that this is new and we're still figuring this out, I think, right? Like what are the right ways of instantiating these symbols for probabilities? I think there's a lot of design space here that's pretty interesting. And some of the other work in this space is going to have different choices about how to define each of these little things, right? So we had one. The definition of disjoint union is something called independent combination, which was a new thing. And then the heap subset was essentially sub-probability space. And then heap disjointness. Well, let me get back to those. I want to show you the model. Okay, so what's the model? The choice of model is really important. And we're again going to build it by analogy with heaps and stores. Okay, so again, we're going to have a model, and it's going to look like, let me quickly make sure I match notation here really quick. I want to get the yeah. Okay, yeah, okay. So, This is the problem when you have to refer to your notes for the first time after not looking at them for a while. You start to lose track of where you are. I want to match the notation here. All right, can't find it. I'm just going to have to pick notation. We'll live. Okay. So we're going to have this. We're going to have omega E and mu. And this is going to be our new space. Now I need to unpack what these symbols mean. Right? There's actually a lot of interesting data contained in these symbols. And picking those symbols, I think, was actually the hardest part of this project. We tried a lot of different choices here. Okay. So I think the real kind of picture that made it make sense for me was the following picture. So I have a proposition. X follows Bernoulli 1/2. What does that mean, really? Right? What does that mean? It's telling me something about the underlying state space of the program. And there's actually a lot of data that goes into this, right? So there's this ambient thing called the sample space, omega. Sample space. Right? And you can think of this as like it's almost like your heap, right? It's sitting in the background and it's storing all the randomness, right? And out of this thing, there's this random variable x that's true or false. And it's getting some portion of the heap, right? And I'm actually going to cut it in half. I'm going to say, like, imagine this. Let's fix omega to be the unit square. Let's fix omega to be the unit square. Okay. Then I'm going to say x is a random variable that's getting half of this unit square and then that half of the unit square, right? And what this proposition is saying is that the area of this one is equal to 1/2, and the area of this one is equal to 1/2. Okay? That's the meaning of this proposition. So I can kind of unpack my analogy a little bit further. X is behaving sort of like a pointer or a location, right? Somewhere in the background there's a heap, but I don't get to see the heap as a programmer, right? Similarly, in the background of this random variable, there's this sample space thing, but I don't get to see that. All I get to see is x and manipulate x, right? In my programming language, I don't get to peek in the back and see, oh, how did you store x? What was the location of x, and so on. You don't get to see that, right? That's hidden from you. What you do get to see is this pointer x, which is essentially just a function, right? X is actually a function here. And it's a function from omega into the two-element set, right? That's what x is, okay? Which looks a lot like, a pointer in some sense, right? So we have that x is this guy. That's going to be our semantic model, right? It's going to be that the meaning of my variables in my program are going to be maps out of this ambience kind of sample space that I'm going to be essentially, like if I were to run this program, you can imagine I would split this sample space up to carve out some room for x and make this map for x, right? Find some space for x and make it this map. Okay? This is a very peculiar model. It's much more complicated than the monadic or whatever semantics I was showing you. It's more complicated than the distributional semantics. Why are we making it this complicated? Well, it's going to work nicely for defining the case we're concerned with, for reasoning about the case we're concerned with, which is this one, right? Which is this one. I want to allocate some new randomness, right? I want to allocate some new randomness for y. And y needs to be independent from x, right? So when I was working under my heap model, I would pick a fresh location for y, and I would use that instead. Now, what's my notion of fresh locations here? If this is my world, right, I need a way of getting a fresh location out of this world. Some piece of randomness, some random variable whose probability is 1/2 that's independent from the one I've already allocated, right? That's the game, okay? Well, here, I'll draw one for you. if I've already allocated x this way, well, then I'll allocate y along the other slice. Okay? Right? And now I have two independent random variables. They're both sharing the same underlying backing store. Just like how in heap allocating programs, they're always allocating fresh cells in the heap. But I've smushed them into the same space together in a way that captures the structural invariance that I want to hold about this allocation, which is that these are two independent random variables that are each true with probability 1/2. Right? How do I know they're independent? Well, we can check, right? So we'll say x is independent from y as a random variable if it's the case that x, that their probability factorizes. So the probability that x is equal to true times and y is equal to true is equal to the product of the independent probabilities. Right? That's what it means for them to be statistically independent, that their probabilities factorize. Right? So if I were looking up here, what would it be? So the probability that x is equal to true, comma, y is equal to true. Well, in order to get at this thing, I look at the pre-images, right? So I'll look at these pre-images, which gives me this square. This is x equals true, y equals true, right? And then to get this pre-image, x is equal to true, well, that's just this whole thing, right? Right? And then similarly, to get the probability that y is true, well, that's going to be the vertical slice, right? And hopefully you can see that taking the product of these two areas, 1/2 times 1/2 gives you 1/4, right? So it's allocated an independent random variable in the context of this ambient sample space omega, which is behaving like our heap, right? That's pretty much the whole idea. Once you have this idea, you can reverse engineer what every connective should mean. Where do I want to put it? Let's put it over here, I suppose. Okay. So we need this guy, we need this guy, we need this guy. Right? Let's do the disjoint union. Okay. This is going to be independent combination. Okay. So what does it mean for, how do we show that some probability space, like the one I drew for you, how do I show that this thing does the thing I promised? It shows that x follows Bernoulli 1/2 star y follows Bernoulli 1/2. How do I show that? Okay. Well, the picture is going to look very analogous. Right? I have to split this thing up into two smaller things that independently combine to give the bigger thing. Right? So I need to show that I can split this thing up into two independent spaces, one of which models that x is Bernoulli and the other which models that y is Bernoulli. Okay? So let's do that. Okay, I'll split it up this way, right? And notice the data of this thing, which I forgot to write down. There's actually the following pieces. There's S, which is this collection of random variables, right? So S is a collection of random variables. And then we have probability spaces, which are the set omega, E, which is a collection of subsets of omega, right? I've drawn these squares, right? These are the collections of subsets of omega. And then mu is a probability measure, which assigns a probability to each element in E, right? So if you've heard of these before, these are called sigma algebras. But it's not important to know what that definition is. Just think of them as collections of subsets of omega, right? In this case, I've drawn, so in this case, I'll give you an example. For this one, E is equal to this guy, the empty guy, this guy, this guy. And then I think that's it. I think that's it. I'll fix it if it's not right. Okay. All right. So I'm going to split this thing, which is this is an instance of one of these things, right? This is a configuration. Yeah, question.
Can you explain what omega is?
Yeah, omega is some sort of ambient space with enough, so it's an ambient space with enough room to store all the randomness we want to allocate. Just like how a heap is like a infinite set of cells that I can keep allocating fresh values in, right? So I pick omega to be a nice thing. In this case, I made it the inner unit square because I'm going to be able to keep smushing stuff into it kind of forever and keep carving out new independent.
Omega is the interval 0, 1, square.
That's right. Yeah. You could have picked a lot of things for omega, actually, because the unit square is homeomorphic to the unit interval. So like you could have chosen a different one. It's fine, right? But we're going to fix it to be the unit square because we know that one has enough room. Yeah.
What happens if you want to allocate more than just Bernoulli random variables?
You mean like what kind?
I don't know if that's probability.
You want to allocate a uniform random variable. Yeah, you're going to need to be able to come up with a way of carving it out of this space. So it turns out you can do that. There's like classic theorems from measure theory which tell you how much stuff you can smush into an interval. It turns out a lot. So there's a fun fact, which is that this is actually, in some sense, isomorphic to the Hilbert cube. So you can actually really cook up some fun stuff that way. But let's not go there. Okay. So right. Back to the picture. So I want to split this thing up into two smaller probability spaces, right? And each of them is still going to have with them the maps, because these are like my stores, which aren't getting split, right? And I need to show that this one satisfies. How did I do it? Yeah. So the bottom one was y. So this one's going to satisfy y. Bernoulli 1/2, and this one's going to satisfy x gets Bernoulli 1/2. Okay. Well, how do we know this one satisfies y gets Bernoulli 1/2? Well, we look at y, and we look at its pre-images, and we see that they each have probability 1/2. So we're done. Okay. I didn't define this proposition for you, but hopefully you can kind of work backwards to that definition. I'm happy to kind of write it if people want to see it. And then similarly for this one, in order to show that x follows Bernoulli 1/2, well, we'll look at the pre-images for x, and we see that they each have probability 1/2, right? And so we're happy. But that wasn't all that we needed for the definition of star. They needed to be independent as random variables, right? So how do we show that? Oh, well, that's gone now. Okay. So I somehow need an analog to disjoint union. Right? I somehow need an analog to disjoint union. I need something that lets me go from these two guys into this big guy, right? Right? Something that takes two smaller pieces and mushes them together into a bigger one that looks like disjoint union. And so this thing is going to be called the independent combination, and you write it as a bullet because it's actually a monoid. It's a partially commuted monoid. What is its definition? So this guy, you can maybe even by looking at this picture figure out what it needs to be. Right? It somehow, well, it needs to produce a probability measure, right? And well, it needs to produce a probability space, right? So it says, we'll say this one, let's just define it on probability spaces because it's not going to touch the random variables. We'll say omega 1, E1, mu 1, omega 2, E2, mu 2. This bullet is defined to be, well, we're going to keep omega the same. Remember, the sample space isn't supposed to be changing, just like the heap is kind of, infinitely available, right? It's just kind of staying put. But what is changing is this collection of subsets of the heap that we're allowed to talk about, right? This collection of subsets, this sigma algebra is what's changing. What it needs to be is like, we'll use this symbol, this square bracket, which is a lot like union, right? And it's going to be the smallest sigma algebra that contains both. And you need to check that that's a well-founded idea, but it is, right? And then what do we have here? We're going to have this probability measure rho, and rho needs to behave nicely, right? It needs to factorize according to the structure that we had over here, right? So in particular, it needs to be that, let me see, it needs to be that rho of, if I have some event E1 union E2, and this is going to hold for all E1 in E1, boy, I am running out of letters, for all E1, little e1 in big E1, little e2 in big E2, it needs to be that if I take these two things, E1, combine them, that's got to equal mu1 of E1 times mu2 of E2. It needs to factorize along the events, right? And this is what's going to make this a partial function. We're not always going to be able to find such a measure that factorizes this way, right? And that's important because otherwise you'd be able to validate all sorts of stuff you don't want to validate. That's one of the games, right? You don't want, like, for instance, you don't want to be able to show that x is Bernoulli 1/2 star x is Bernoulli 1/2. That would be really weird because the whole point of star is that you're decomposing the probability distribution into independent pieces. If you can validate this proposition, it's wrong, right? So when you're playing the game of how do I design a probabilistic separation logic, you want to be thinking about these examples. And every time you have a proposal, you'll be like, okay, why is that one true? So this is a great exercise. Show that you cannot find a you cannot find a factorizable measure that validates this proposition. That's really important. Yeah.
But just wanted to ask, why do you talk about rho equal union? It feels like intuitively, and maybe I'm okay, that it should be intersection, not union. Like,
I think you might be right. I might need to look at my notes here. Let me think. Because yeah, I think it should be intersection. It is intersection. Yeah, you're right. Thank you. Yeah, it is intersection. Yeah, good. Yeah,
the E definition that you draw.
yeah.
Every element of the set. You've drawn it as like squares with lines in them, but
Yeah.
that really is just the set of like the smaller rectangles that make up a range, right? Like the first one is the set consisting of the top left square, the top right square, and the bottom
You mean, what is the definition of E here?
What is the definition of the elements?
Yeah, so I've actually drawn an example here. This is the definition of the element of E. And then when I find the smallest sigma algebra that contains this guy, so then what will E1 and E2 be here? They'll be the events that and that and that and that. And then the smallest sigma algebra that contains both will actually be this set again.
But the way you've drawn it, that's just like what are those objects actually?
They're sets. They are sets, yeah. So this is actually the collection. You know, if I label my axes, let's say that, I don't want to call them X and Y, but it's literally the collection of points in these two halves. Yeah. Yeah. There's a lot of ways of cooking this up, by the way. This is just one that's nice to draw. In practice, you don't have to draw it this way at all. It just needs to satisfy this intuitive idea. And by the way, these should be rows. These should be rows. They need to factorize. Yeah.
Is there like a nice way of choosing an appropriate omega for a given program?
Sorry, say it again.
Is there a nice way of choosing an appropriate omega for a given program?
Is there a nice way of choosing an appropriate omega? I like this one. I mean, that's a bit of a pithy answer, right? But actually, it's a really good one. Just like how, you know, that's like asking, how do I choose the kinds of heap shapes for my programs? Right? Well, okay, well, I clearly want to have a countably infinite number of heap cells that I can keep allocating to. And so this is a similar kind of object. It's like a very large set of possible like intervals that I can carve out for my new randomness. Right? It turns out that the interval has, because it's like there are real numbers involved, it behaves very strangely. There's just so much space inside of the interval that you can just keep carving out fresh copies of randomness as much as you like. It's a very cool property of the interval, actually, that you can do that. Yeah. I'm confusing myself. So it's saying this is a partial function that factorizes in this way. I think it has to be mu. I think it has to be mu. Yeah. Yeah. It's a fun game to try to figure out which definitions make sense, actually. Which one?
The row intersection down there, because E1 cross.
For all events in E1 and for all events in E2.
No, I mean like across the right.
This one, this is supposed to be times, like product. Yeah. Questions?
Can you give a definition of mu/rho?
These are probability measures, so they are functions from the set of events to intervals, or to a number, right? So mu is a function from events to some value in the interval 0, 1. It behaves like a probability distribution. Yeah.
An event is just like one element of each of those subsets that's in E.
Yeah.
How can we join this with all of this to another axis, another z?
You're saying, how can we add another one?
Yes, x disjoined with 1. How can we add another z?
Oh, you want to allocate another z that's independent here.
How do we
Ooh.
how do we say?
You need to be clever. And so I don't know if I want to draw that. That's an interesting exercise, trying to come up with another fresh source of randomness in the square. You might not be able to draw it as nicely. You might have to pick out disjoint subsets. Yeah, it gets kind of nasty, actually, if you want to allocate another one, I think. I could be wrong. I haven't actually drawn that. Maybe there's an easy, clever way to do it. Maybe if you just chose perpendicular. Yeah, maybe there's some clever way. I don't know. Someone can think about that. That would be interesting. OK. Right. So this thing here, this independent combination, the fact that this is a function, meaning that if there exists such an object over here that satisfies this, then it's unique, which is a pretty amazing fact that required a kind of interesting proof, actually. But it's a function, which is kind of interesting. OK. So this is our picture, right? So what do we have? Well, now I can write, well, did I erase the interpretations? Well, I've told you essentially now what this guy means, this disjoint union, right? It's going to be this partial function that takes two probability spaces and tries to combine them into one that satisfies this factorization structure that you want to have. So it behaves a lot like disjoint union, right? It looks a lot like disjoint union. I'm taking two smaller probability spaces, mushing them together into a big one, and preserving the measure factorization structure, right? So that gave me my interpretation for disjoint union. So we're actually done with that. By the way, this is, if you want to go stare at a definition, this is in the paper. It might be better to read than on my Blackboard. Okay. All right. So now I want to kind of pause and say, like, what does it mean that, that this proposition models X? Well, it's actually very important that I can pull back X into some well-defined subset over here, right? And let's see why it's the case. So let me define S omega E mu models Bernoulli theta. I'm going to define that for you now. So if and only if the pullback of S, so we'll say S inverse, sorry, there needs to be an X here, S inverse of X equals true, right? So S inverse of X equals true, well, that's like, if this top one's true, that's this set here, right? That has to be in my event structure, right? That's first requirement. Then I need to be able to pull back. That needs to be in my event structure, right? Because remember, I defined my probability measures on events. So I'm not even going to be able to compute the probability of stuff unless it's in my event structure, right? And then I have that mu of S inverse true, that's got to equal theta. In the paper, there's a bit of extra jargon around this to handle stuff like free variables, but I'm just showing you kind of a simplified version here. Okay, so essentially what it means is that I need to be able to, I need to have the events for these random variables in my essentially the parts of the heap that I own, right? Like if you're thinking about ownership as like my heap has locations in it, well, now ownership is like my heap has the events that I need to compute probabilities of things, right? So this kind of leads to a cool intuition, which is like ownership is what's called measurability. Because this condition here is called the measurability condition for a random variable. If you like probability, this is literally the definition of X being X is measurable. I won't dive into that definition, but it's an interesting thing. So you can see how we've kind of baked in some very well-founded ideas from probability. I mean, this is all probably very new. At this point, I'm just kind of blasting. I'm hoping that you guys are at least enjoying seeing a bunch of new stuff, right? But so this is a well-known probability definition, this measurability, and it's nice to see that in our logic, right? Because probability theory is very well studied. So if we can take ideas from probability and make them evident in our logic, it makes it easier to apply well-known probability theorems and ideas to our logic because it's kind of in there already, right? So we'll be able to say things like, okay, well, if I own a random variable, then it's measurable, and therefore its composition with measurable functions is measurable, and therefore I can compute probabilities of it, and therefore I can compute expectations of it. Like suddenly you get a lot of very nice structure because you know that this thing is measurable. So that was actually a very important piece of the puzzle. Yeah.
Is S inverse of X equals T a complement of the one X equals F?
Can you speak that louder?
Is it a complement to the S inverse of X equals T and S inverse of X equals F?
Which part is the complement? Are you asking?
Are they both complements of each other, or
Oh yeah, I mean this is specialized to this particular case.
Okay.
So if I had, I was asked earlier, what if I wanted to have more kinds of random variables here? You would need to define this different. You would need to be like, for every element, so I can give you the definition of measurability, but essentially it's the requirement that for every element in the codomain, its preimage is in the set of events. So in this case, I just enumerated the elements of the codomain for you and wrote down that that was in the event structure. Yeah, cool. Okay, so that's pretty much the core idea of the model. And hopefully the picture of it is at least a little bit clear. I think there's a lot of new stuff up here, and it'll take some time to digest. But I think really the point I want to make is that every single piece of this is in really close analogy with standard separation logic, which is kind of nice, right? Like, the store, this looks a lot like a normal store in separation logic. It's a map from names to random variables, right? So S is a map from names to functions, omega, arrow, some codomain D, where D is a value, right? We can even call this values. Right? That's what S is, which looks a lot like a store, right? Except instead of these being values, now they're random variables, so that's okay. Right? And then this thing looks a lot like a heap because it's kind of being implicitly manipulated as I'm running my program, but it's only kind of observable via looking up things through S. Right? Yeah.
This might be a dumb question, and I don't really know separation logic, but is there an analog of conditional independence?
Ooh. That's very fun. What a nice question. Yeah.
Like I could think about two heaps being like having some overlapping layout, but if you know some other tag or configuration, it tells you that you don't actually care about the overlap or something.
Yeah, so the question is, what about conditional independence? I'll leave it at that. There was a lot of the question there. But that question I think I can actually give some answer to. All right, I'll just sketch it. Conditioning. We've talked about conditioning and how important it is. It's such a critical component of probability and probabilistic reasoning. We think it belongs in the logic, right? So what you would like is something that looks like this. Ish, right? I have this symbol, CX gets X, and then a proposition P. And I want this to mean something like this. It means P holds conditionally on X. We want that. So we can say things like, if I have that like X gets big X, and then I have like Bernoulli 1/2 star Bernoulli, or X follows that, Y follows that. I want that to mean that X and Y are conditionally independent given, or this should be Z. Given big Z. Yeah. So that means that X and Y are conditionally independent given Z. And this guy here behaves something like a modality in our logic, where we're allowed to just kind of stick it inside of propositions, and then terms get a new interpretation under the modality. Right? And that interpretation is literally holding conditionally on an event. And giving a semantics to this thing is very spicy. Very fun. But if it's discrete, it's not as bad. If it's continuous, it's really, really bad. But it's very interesting. Right? So in our paper, this lilac paper, I remember the title now, a modal separation logic for conditional probability. And this was like one of the big things we wanted to handle, was this ability to condition within the logic. Conditional probability. So that's pretty much it. I don't want to say too much more about that. It gets pretty into the weeds. Yeah.
Does it behave like diamond?
Ooh, is it eventually? Yeah. Wouldn't that be cool? In the paper, we actually do study a few of its properties. So like, does it behave like always or eventually or whatever? A few of them, not all of them. So we wanted to show it was like S4, but it's not. Yeah. So that would be cool. Maybe there's a better way. I actually think that's like an interesting open question, honestly. It's like, first off, I don't think this is the only way to do it. So there's a paper from Jialu Bao, this Bluebell paper, where they actually have a different way of defining a conditioning modality, which has a different structure and probably therefore has different modal characteristics, which are kind of cool. And it would be cool to find ones that have particularly nice ones, because then you can commute it around and do things with it, reason more compositionally about it. For our purposes, we just kind of proved very laboriously the specific rules we needed to show examples. OK, that's not so great. It would be nice if there was more structure there. So I think coming up with the right characteristics for manipulating these conditioning modalities is quite interesting and could potentially be quite useful. Any other questions? Cool. Yeah, so I really have to credit John with these ideas. I mean, I feel like I'm just following him along. You know, this is a lot of his stuff. OK, cool. Any other questions? Great. OK. I wanted to conclude with some perspectives. Well, first off, thank you so much for inviting me. This was a lot of fun. This was actually my first time going to OPLSS. So it's interesting to be here. You guys have a very nice workshop, I got to say. Or what is it? You know, summer school, right? It's amazing. It's been going on for 20 years. And I think generations of students have really benefited from it. It's really something. So it's amazing to be a part of that. I wanted to conclude with kind of the big challenges in probabilistic programming. Because I think we should use these things and we don't yet. So why not? I think really one big challenge, of course, is scalability. Right? And we have this underlying hardness, which I showed you, which is really hard to avoid when you want to compute the probability of things happening. Right? So I'm hopeful that maybe some kind of deductive logic can help, some kind of tractable target can help, better sampling can help, right? But I think this is going to be a problem that requires many different solutions working together, right? Because fundamentally, you're not going to avoid that hardness. You know, it's going to be there all the time. So in order to make effective probabilistic programming languages, I think you're going to need kind of a synthesis of a lot of ideas, right? This is something that really has made me more excited to learn more about programming languages things, because there's so many ideas within type theory and type systems for interesting ways of constraining programs, and so many ideas from semantic models of ways of structuring the space of possible interpretations of programs. All these things are very useful, I think, for studying this problem. So I think it's very important and very interesting. And it's really a barrier for using today's probabilistic programming languages. They just really don't scale well. And when I mean that, I mean like I don't know of a single probabilistic programming language that's probabilistic program in the wild that's more than like 1,000 lines. Right? So like right now we're on the order of 1,000 lines, maybe, if you're lucky. We should definitely try to get to some bigger programs, right? Usability. Today's probabilistic programming languages are not very fun to use. And they're not very fun to use on every level of interacting with them almost, right? From the fact that the IDEs don't have syntax highlighting, well, okay, that's not so bad. But like, you know, there's no debuggers, there's no profilers, there's not even really tools like that tell you when the program's going wrong a lot of the time. They'll just output a wrong answer, right? So they're often buggy. And And I would say that today, probabilistic programming languages are the domain of the experts, right? Like, really only experts today can use these things, which is kind of not the point, right? The point is you get to write down a program, and the system just tells you something, right? Tells you the probability. Yeah.
In terms of these usability challenges, how much of this is engineering work and how much is just like,
Oh, I don't know how to do this. I think there's really interesting research questions here, right? Like, you know, I have an assertion I want to hold about my program, and I want to do replay to figure out what caused me to reach that point. And like, that's a real systems challenge, especially when this is situated inside of a high performance inference strategy that's doing some crazy stuff with knowledge compilation. And you're trying to step inside and be like, why is this thing happening? It's pretty tough, actually. Ideas from like incremental programming might be useful here. Ideas, yeah, there's lots to do here, I think, that would be very interesting. Right? Profilers are obvious, but I still think it's very interesting research, right? Because what is the nature of profiling in a probabilistic programming language is not obvious. Is it the runtime? Is it the convergence rate? Is it the whatever, right? There's different correctness criteria here that we care about, and they're kind of complicated and interesting, right? And they're not standard. Right, I think you could go on about usability. I think there's really core semantic challenges. And what I mean by that is, you know, the denotational side, right? Like, I give you a language, and I want to associate that language with something that looks, feels, you know, walks and talks like a probability distribution, right? So I want something that's like, you give me a term, and then out comes prob, something that looks and behaves like a probability distribution, okay? It turns out this is just so hard, right? I showed you a very, very, very restricted language, right? I showed you tiny people, which doesn't have loops, doesn't have continuous probability, doesn't have a lot of features, because it let us do this, right? We were able to write down like a nice denotational interpretation of every term. Okay, well, what if I add higher order functions? Lambda x dot e. Okay, that might be okay, right? Maybe I have only coin flips and I have higher order functions. Maybe I can cook up a way of doing this, right? And maybe this is like some kind of, you know, you can start thinking about category theory, right? Maybe is this a Cartesian closed category that has internal to it a model that's simply type lambda calculus? Maybe, but then what if I want to have recursion? You start to really hit interesting and complicated semantic domains. And there's actually some really nice work from State and others on pushing this boundary for what kinds of semantic domains we can have. Because sometimes it's really nice to prove things about your programs using a denotational argument, right? Like we saw a lot on using syntactic arguments to prove things with logical relations. But what if you want to use probability theory to make an argument about your program having a property? These are probabilistic programs. Maybe you want to use some well-known fact from probability, like, I don't know, Definetti's theorem or something, right? Well, that's hard to make a syntactic argument out of. It's a property of a probability distribution. So it's really nice to be able to dip into probability theory sometimes to make arguments about your program. And if we don't know what these models are, it's really hard to do that, actually, because, you know, we don't even know. Yeah, I mean, and this one of the challenges here is that, you know, this thing has very poor structure, actually, as the languages become richer, as you add higher order functions, if you add continuous probability, these things become super degenerate. So trying to recover more interesting structured spaces here that let us make probabilistic arguments without having to learn what a Grothendieck topos is would be nice, right? Because this is really hard to make denotational arguments about, but we know lots of probability theory. So there's this gap, right, between the lots of nice theorems we know about probability and making arguments about programs using those theorems that I think would be really nice to have a better answer for, right? It would be great if we could have a better understanding of this picture. I think that's open. I don't think we have solved the problem here. Right, and then I had kind of one more. And then I wanted to talk about just inference in general, which I guess falls under performance, but I feel like I wanted to give it one last shout out. You know, I only showed you a tiny sliver of the huge world of very high-powered probabilistic reasoning tools and capabilities that have been developed over the years. There's lots of Markov chain Monte Carlo methods. There's other kinds like variational inference. These are terms I'm just going to throw out. There's more knowledge compilation. And there's different ways of making these things interact within your programs, right? I think that these things, each one of these little circles is just absolutely crying out to be like PL-ified, right? Because they're really complicated, right? These things are very hard to reason about. And then when I'm trying to make a programming language that does inference by using Markov chain Monte Carlo, it's like, well, it's going to have bugs, right? And you know, we don't really have what I think of as good foundational reasoning principles for these. So I showed you like this thing, sigma gets E rho becomes V, right? This is for direct rejection sampling. Remember this guy. There's a reason I showed you only this one. Because as it gets more complicated, well, it becomes a lot harder to give nice inductive judgments that describe these things. Like Markov chain Monte Carlo almost has like a co-inductive flavor. It's very strange, right? It would be great to have a better operational understanding of what these actual strategies are doing so that we can formalize them more easily within our systems. I think that that's something that is just waiting to be done. I mean, this would be really useful to have. And there's been some work on this. I mean, you can find approaches for doing some of these things, but I think it's still very active. And every year at POPL or PLDI, you'll see a paper or two that's poking at these problems. OK. So with that, I don't have anything else. That was all that I wanted to say. So I'll take a few questions here for the last few minutes. Yeah?
Jumping back a little bit, are we able to like combine the probabilistic separation logic with regular separation logic to reason about probabilistic programs with heaps?
That's a really fun question. Yeah, the question is, can we combine heap manipulation and probabilistic separation? That's a really cool idea. I don't see in principle why not. In practice, it'd be hard because you'd have different notions of separation. And they would have to be working together. And I'm sure there's lots of work on that with concurrent separation logic. That would be where I would look. Because if you want to have a concurrent heap manipulating program, you might have a notion of thread disjointness and heap disjointness that you're trying to track. Something from there might be useful. I also think concurrency and probabilistic separation could be quite interesting, right? Because a lot of practical probabilistic systems are concurrent, like in distributed systems, for example. So it could be useful to reason about concurrent separation logic in the context of this separation as well. Yeah, it's not. I'm not working on that. Yeah, so that's interesting. Yeah. Any other questions? Yeah.
So do you think there's no, in the perspective, you don't have a part about reasoning, like you presented lilac, then you talked about bluebell?
Oh yeah, sure. I would add.
I guess there are challenges, but do you have? What can?
That's a great point. Yeah, I should say like, oh yeah, this is non-exhaustive. Yeah, there's a lot of challenges, right? So definitely with reasoning. I mentioned a few as we were going, right? And maybe I'll comment on a few that I can see. So one is automation, right? So like, what does a decision procedure for lilac look like? I think that's pretty interesting. Another one is integrating it with other kinds of separation. That's pretty interesting. There were definitely there's lots of others. I feel like yeah. I mean, it's so new. I almost feel like it's hard to enumerate, right? You can go look at the trajectory of separation. Like for example, like separation is often too strong of a requirement, right? Most practical mutable data structures, separation is way too strong, right? Because it's like no heaps can touch. So that's not how practical data structures are. Right? So there's like certain kinds of reasoning principles about separation logic that you need to add in order to reason about practical mutable shared state, right? And the same thing happens in a probabilistic context where I have, you know, not perfect separation, but controlled separation. And what are the reasoning principles for actually incorporating controlled separation into probabilistic separation logics? I think that's really interesting. And we'll probably use ideas from probability theory that we use for decomposing state and things like that. So that, especially in combination with the conditioning modality, becomes a really, really rich question, actually. I think that's quite interesting. Yeah.
say, make deterministic my probabilistic programming language by like choosing only Dirac distributions for my probabilities.
Okay.
Do I get ordinary programming languages, or do I get something else?
You mean in the context of this logic? Like
Yeah,
if I just had, like you're asking, does this degenerate to vanilla separation logic?
Yeah.
That's a fun question. I haven't thought about that. If someone can prove that, let me know. That would be really fun. I bet it morally feels like it should. That would be really cool. Yeah. Yeah.
You were talking about earlier using factor probability to like reason about your program. Has there been any work on like integrating or like embedding probabilistic programming like a theorem server so that you can sort of like optimize programs and implementation?
Okay. The question is, has there been work on incorporating probabilities into theorem provers? And what was the end of the question?
As in like in relation to what you said earlier about like optimizing or like reasoning out a program using theorems for probability.
Oh, sure. I don't know of much work that actually tries to, so there's definitely work in trying to reason about probabilistic programs in theorem provers, right? Like Joe Tasserati has a lot of work on this. There's lots of others that do, right? So then I think there's the fun question or funny question of what if I tried to bake probabilities into my calculus constructions? That'd be pretty interesting. I don't know what the properties of that would be. But maybe internal to that language, there's free theorems about probability that you could make use of. That would be cool. Oh, sounds like fun. OK, cool. So that's it. So thanks again, you guys. You were a great audience. This was a lot of fun.